pressed record. Okay, here we go.
Yep, I see it now.
Now you see it? All right, we're good to go. Okay, so next week is finals week, right? So I'm just going to write this in. Finals next week. Okay, so that throws a few wrenches in our system, meaning your homework is not due next Wednesday. This homework that you'll have today is the lab is due on Friday. All right, it's due on Friday. Okay, so next week, I'm going to provide the finals next week. So the schedule. My goal is final available. On Tuesday morning. Due on Friday at 11:59 p.m. Okay?
Yeah.
All right. So be comprehensive. Remember the deal we made. Or if you do better on the final than you did on the midterm, that grade will erase your midterm grade. You'll get the same grade for midterm grade as you did for the final. If you do worse on the final than you do for the midterm, I won't punish you for that. You see what I mean? So that's not how it works. It's all value add for you to do better on the final, for you to give it your all.
So is the due on Friday at 11:59 p.m. both the lab and the final? It's like the final Friday after this Friday?
Yeah, good thing. Lab is due on this Friday and due on Friday next week.
So 4 days to do the final, basically. Cool.
Exactly. So you bring up good points that I don't think of. So that day, this is 3/19/21, and this one is 3/11. No, it can't be 11. 3/12. Yeah, 3/12. Tuesday morning. When I say Tuesday morning, this day is what's that, 16/21? Yes. Tuesday morning, 3/16/21. So when you wake up in the morning, I'm sure I beat you guys up. Meaning not beat you up literally, but beat you by waking up. That what are those called? I forgot. But yeah. So is this understood by everybody?
Yes, sir.
All right, good.
Right on.
Right on. End this class with a bang. Okay, so now we're going to get to our last thing, which is the most difficult thing to understand. I have to say that. It is one of the hardest things to understand. It was very difficult for me to understand. And that is the second law of thermodynamics. So we're going to define and state the second law of thermodynamics. The second law, we're going to use the second law to determine the maximum possible efficiency of a system. Maximum possible. We're going to look at a system, conduct an analysis using the second law of thermodynamics, meaning max efficiency. This is the only part of the second law of thermodynamics we're leveraging, is max efficiency. Given a thermodynamic system, we're going to describe the methods using the maximum efficiency of a system. There's another part to the system, and you guys understand it a little bit, but we're not going to dig into it too much, because I believe if I have to teach you something, it should be what we're going to learn today when it comes to the second law of thermodynamics, because it's the governing principle of it. So what is the second law of thermodynamics? You could read this very, I guess, convoluted explanation. Isn't it possible to construct a device that operates in a cycle and produces no effect other than removal of heat from a body at one temperature and the absorption of heat of an equal quantity of heat by a body at a higher temperature? So what it's really saying, it's impossible to move energy from a body at a lower temperature to a body at a higher temperature that doesn't produce any other effect, meaning moving that energy from a body at a lower temperature to a body at a higher temperature takes extra work. You can't just move the energy. So that simple thing of you can't move energy from one body to another without producing other effects, other energy losses, more energy must be put in than you get out. It causes many different things, but it is a law. It's a simple law, but at that same time, the simple law causes many things that are not simple. So all energy put in a system cannot be converted to work, period. No matter what, all energy put into a system cannot be converted to work. And one major thing that really governs a lot of this stuff is that heat transfer always occurs in one direction, from hot to cold. So no matter what, the law is more important or more all governing and omniscient than taxes and anything else, is that heat will always travel. There's no way to stop it, ever, ever, ever. You can insulate it, you can slow it down, you can make it less, but since we are made of matter and heat is the measure of movement, everything in the world, in the universe as we understand it, is cooling down. Everything is cooling down. So energy always travels, heat always travels in one direction. It always travels cold from hot to cold. Why? Because everything is cooling down, everything. So this governing principle of the universe and physics as we know it makes the second law so powerful. So what we use two really concepts to deal with the second law of thermodynamics. One of them is entropy. And the reason why I'm not going to dig into entropy a lot, because you guys understand it, entropy, we'll learn a little bit more about it today, but it's really just a measure of unavailable heat. It's just a measure of heat losses. And that's what we use it for. But there's another governing principle above entropy, and that is what we're going to learn about and you'll be tested on. So we've been through this again: isolated, closed, open. Everything really isolated and closed systems are really special cases of open systems. That's how you can look at it. We've been through this already, though. But now we're just going to talk about entropy. Remember what entropy is? The change in Q with the change in T absolute. When I say absolute, it's in Rankine when it comes to the British English units. This is, as you can see, this is the amount of heat added to the system during the process, right? So if you add heat to a system during a process, like you're making the system get hotter, right? Well, just think about it. You're fighting the current of everything is getting colder all the time, right? It's like you're walking up a river that everything is going, pushing against you, but you're walking something up a river. So no matter what, it's going to take you more energy to walk up that river than the energy that you will deliver to that point in the river. I don't know if that just confused you more, but I just thought of that and I thought it was brilliant. I'm going to use that one again. Does that make sense?
I feel like it does.
You feel like
Yeah.
it does?
Yeah.
Okay.
Yeah, it does.
All right. So the change in Q, when you move something, you add heat to something, there's going to be a loss. And that is how we measure enthalpy. And so how far did you move it? How hot did you make it? From what temperature at the bottom did you move it from up to the temperature at the top? And since you had to fight against the current, therefore you caused the amount of energy it took for you to move it is entropy. And as we've talked about before, T absolute. And why is it T absolute? Because there's literally no movement at 0 Rankine. There's no heat. There's nothing. I think the only place that we know is 0 Rankine is like in space when no light is touching anything. So like if you're on the backside of the Earth and the sun is in front of it, that's where it's 0. Another way that we can look at this is the second law can also be expressed in the change in S. It's greater than 0 for a closed cycle. In other words, entropy must increase or stay the same for a cyclic system. It can never decrease. And I will argue that entropy must increase. This stay the same. I've never seen a system that's going to stay the same. But that's what they said in the book. So I'm still trying to think about what system is just going to stay the same. Now, the entropy can be very minor and negligible because you've insulated the system so well, but entropy is always increasing, period. It might be microscopic increases, but it's increasing. So this term down here is how we've used, and I'm going to tell you the truth, investigation by substance. I'm sorry. So this is how we learned how to implement the first law of thermodynamics. We haven't used entropy much. I did throw a little curveball, a wrench in your system in the midterm because I wanted you guys to see how much increase in the entropy happens when you're in you're in places where you don't need to increase temperature. And I can explain that more here in a little bit, but I wanted you to see it. But in actuality, so we have been investigating by substitution of reversible processes, adiabatic processes, for actual irreversible processes to aid the student in the second law of thermodynamics. That's what it says in the book, but I'm going to tell you the truth. I still use adiabatic processes to calculate things, especially as an energy engineer. I do a lot of building energy engineering, so I'm thinking about the entropy of a compressor loading up refrigerant is something that's so minute and microscopic that I actually ignore it, and it's so small. But I'm not looking at power plants. I'm not looking at big renewable energy plants. I'm not looking at cogeneration or anything like that. But for my profession, I still hardly ever leverage the second law of thermodynamics. So what you have learned in this class and these concepts are transferable. It's not like you're missing anything. Well, you are missing something, but it's not, you can learn it on the fly. And so I do use these diagrams in my profession. The enthalpy, I use the enthalpy diagram and the temperature entropy diagram used for analysis. It's saying actual or irreversible processes cannot be drawn since there's not a succession of equilibrium conditions, but they do have other diagrams, which is one that I use often is a pressure versus enthalpy diagram. And that diagram has it has entropy lines, so we can use them if we want to. So all of this isn't totally true, but it's just good to understand that you can use the first law of thermodynamics even without entropy and come up with good approximations of what you're trying to do. But what we're going to learn about, so that's pretty much all we're going to learn about entropy. You understand it always travels from hot to cold, no matter what. If you're moving a body from a colder place, if you're moving heat if you're adding heat to a system, period, you're fighting a current. So if you're fighting that current, it's going to cost you. So since it's going to cost you, entropy is involved. But the Carnot principle is really the judge when it comes to how efficient you can be. It's the judge. So Law Carnot, I think is crazy. In 1824, advanced the study of the second law by disclosing principle consisted of the following propositions. And this principle is the law, and I don't know how he thought of it, but he did. And I just like Einstein and Euler's formula, they're magical people. So this is what we're going to focus on for the rest of today. We're going to do 2 examples, and then I'm going to let you loose, and you guys can work on your lab, get stuff done. So the basic concepts of the Carnot efficiency is that you cannot be more efficient. Any process can be any process when it comes to transferring heat. You cannot be more efficient than Carnot efficiency. In Carnot efficiency, you're thinking of, well, what does that mean? Well, that's the maximum amount that's the biggest percentage of energy you could transfer based on the hot temperature and the cold temperature of where you are at, period. So you can see number 1 here and through 3 is that an engine can't be more efficient than a reversible engine operating between the same high temperature and low temperatures. Here, the term heat reservoir is taken to mean either a heat source or a heat sink. So an engine can't be more efficient than its heat source and heat sink. The delta between them, like I said here, the difference. This difference. This determines its maximum efficiency. Okay. So even if it's reversible, but remember, we're dealing with entropy, which is that governing omniscient power that says everything will get colder from here on out. So entropy makes it so that no process is reversible. But even if you consider a process reversible, it cannot be more efficient than its temperature hot and its temperature cold. And we'll see how to use these two different, the heat source and the heat sink. So it keeps saying the efficiencies of a reversible engine depends only upon the temperature of the heat source and heat reservoir. So they keep mentioning this reversible thing, right? Because they don't want you to think about entropy. But so they're telling you, hey, there's another law within the second law that governs efficiency. And when it comes to systems that we want to produce work or power or anything like that, this law governs you at whatever conditions you're at. Let's see. So for example, so maximum Carnot efficiency is the maximum temperature at 0 degrees R here. So that's 0 degrees R. And this would be, I don't know what the maximum temperature ever observed is. So that's the maximum efficiency that you can get to. But since in Rankine and the temperature and the units are designed to produce an efficiency, but since we're never at 0 degrees R and we're never at like the temperature of the sun, we're always thinking about what is our maximum temperature at the place where we're trying to make the process operate. Okay, I'll continue. All right. So we're going to demonstrate this in a simple cycle and examine the proposed heat power cycle that consists of the following reversible process. So we're going to go from 1 to 2. This is adiabatic compression from temperature cold to temperature hot due to the work performed on the fluid. So here's temperature cold, here's temperature hot. So work is performed on the fluid. So we're compressing a liquid. And so as we compress the liquid, the temperature increases. All right. So then they wanted to make sure you understood this is an adiabatic compression cycle. So that means that there's no entropy loss. We're not even worried about entropy. Then there's isothermal expansion, as the fluid expands when heat is added to the fluid at temperature hot. So isothermal. So heat's added to the fluid at temperature hot. The fluid is expanding, but it's not getting hotter, right? But the reason it's expanding, so the enthalpy is changing, the internal energy is changing, but the temperature, the sensible heat, the temperature of that fluid is not changing. So expansion, expanding. Okay, so then from 3 to 4 is adiabatic expansion as the fluid performs work during the expansion process. So from here to here, this is where you can say, here are some examples of what's happening here. A piston fires, or it turns a motor, or it turns a fan. This is what happened with the expansion. So, but the expansion, the amount of work that can be done from here to here is governed by the temperature cold and the temperature hot. So the compressed liquid got raised to the hottest temperature available. That's it. That's the highest it can go. All right, then isothermal compression, as the fluid contracts when heat is removed from the fluid at a temperature cold. So this is the Carnot cycle, but everything is governed by the hot temperature and the cold temperature. So as I've already stated, it's known as the Carnot cycle. And the heat input in the current is graphically represented in figure, where's figure 21? This is figure 21. All right. Here, as the area underlined by 2 and 3. So we'll go back up here, and this is what they're talking about. This 2 and 3. This is equal to QH. The heat rejected is represented as line 1 and 4. And as we've talked about, this is where the compressor, it was compressed and it was being cooled down. So the difference between the heat added and the heat rejected is the net work, the sum of the work processes, which is represented as the area of the rectangle 1, 2, 3, 4. So here is the work. So if you multiplied this side, let's say side 1 times side 2, if you did side 1 times side 2, that would equal work. But the efficiency of that work, notice it's equal to Q hot minus Q cold divided by Q hot, which is the same thing as temperature hot minus temperature cold divided by temperature hot, or 1 minus temperature cold divided by temperature hot. This is known as the maximum impossible, I wrote that in, cycle efficiency. And all the temperatures are in R. If you put them in Fahrenheit, you're not going to get the right answer, because you're always dividing by temperature hot. Here, I mean, you might get the same delta on the top, but you won't get this right answer on the bottom if you don't use Rankine. All right, so here we're going into problem number 1. An inventor claims to have an engine that receives 100 BTUs of heat and produces 25 BTUs of useful work when operating between 140 degrees and 0 degrees F. Is the claim valid? Okay. So let's go through. What's the problem statement?
Is the inventor's claim valid?
Yeah. Is the claim valid? What systems are involved? Well, we have an engine, right? Okay, we have an engine, so I'm going to draw that as a little, one of these little things. I don't know how else to draw them. I used to draw engines. Okay. Produces 25 BTUs. So this way, I'm going to say this is 25 BTUs. And we're going to say in to the system and out. We're going to say 100 BTUs. All right, but then we're going to say this temperature here is a hot temperature that's going in, and that is temperature is equal to 140 degrees F. And then they're saying this temperature here is 0 degrees F. All right, so that's the system involved, right?
Yeah.
Okay, so what's known? What's known about this system? We know temperature. These are, so this is claim. Let me see something. All right, this is the claim. This is the system involved. Here's our known versus, put these unknown. What's our known versus unknown? We know temps, right?
Yeah, we know temps and then the energy going in and energy produced.
Right. We're saying energy going in and energy produced. I'd agree with that, only though we're trying to see if his claim is valid, right? Is the claim valid? So temps are known. We can say input energy unknown is efficiency. This is so these are nouns. So these are unknowns. Is efficiency. And output energy. Well, what assumptions do we have? We can just assume straight up that this system is adiabatic. Adiabatic. And we can also assume it's isothermal. It does not exchange anything with the outside air. And we're talking about this system includes temperature hot and 0 degrees and includes the hot and cold temperatures. Okay.
Yeah.
So other than that, we're assuming, hey, it doesn't exchange any thing with the environment, no heat transfer with the environment, and it's reversible. So it's adiabatic. Those are our assumptions. So let's solve. So we have Q on the hot side. So if you think about it, what we just talked about previously, we have Q hot. We have Q cold. On the cold side, that is what the temperature is being produced. So you could say that you have it, but we're trying to figure that out. So we have T hot and we have T cold. So Q hot is 100 BTUs. T hot is Rankine, I think it's 460. So T hot is 140 plus 460. That is equal to 600. And then T cold is 460. So then, what do we do? What do we do with this information to find out the maximum efficiency? We go back to here and we use this equation. T hot minus T cold divided by T hot. So 600 minus 460 is what? 120. Divide that by 600, what do I get? .233333, right?
Yeah.
0.23. So that's the maximum efficiency, all right? So let me ask you, can he produce 25 BTUs on the cold side?
No, because that's
No.
more than 23%.
Exactly, right? So Q cold is equal to 223 BTUs. So unless he changes the law of physics, and there's a movie when it was that just came out about entropy and going backwards and stuff like that. What movie was that? It was like Towers. Or what?
Tenet?
Tenet.
Yes, exactly. Unless he's in Tenet, he can't do this. Yeah, so this is impossible. So no, his claim is not valid. Claim is not valid. Okay. All right. So now we're going to move on to the second example, which is the actual versus ideal efficiency. So for this one, I think I have one. Yeah, we have two for it. So we can move a little further on this guy. I plan for this one. Okay. So if we read the question, the actual efficiency of a steam cycle is 18%. The facility operates from a steam source of 340 degrees and rejects heat to the atmosphere at 60 degrees. Compare the Carnot efficiency to the actual efficiency. All right, what's the problem statement here?
Just comparing the actual versus the highest impossible.
Yeah. comparing efficiencies. That's what I'll put here. All right. Describe the systems involved. Well, it's the steam cycle. So you can draw a little picture. Here's the source. One like this. We'll make it simple. So steam goes from here, goes into little turbine, comes out, goes to a condenser, comes out, goes through a pump, comes out and goes there. So there it is. And then we know, okay, this efficiency is 18%. What else do we know? We know that T hot is equal to 340 degrees F. We know that T cold is equal to 60 degrees F. And we do not know the Carnot efficiency. We know this is the efficiency, the actual. Okay, so what is known and unknowns?
A
We know the-
known. Good.
Go ahead.
We know the temperatures.
So we know T hot, we know T cold. These are knowns. Okay, we know temperature, we know T cold. We know for this problem, we know efficiency. The actual efficiency, right? And I mean, based off what we're doing, and you know, we're all professionals now. We know what we're doing because we've been doing thermo for a while. We do this stuff. We don't really need to know any more than that. Like those are the unknowns, like what the flow is, what enthalpy, what internal energy, pressure, all that other kind of stuff. We're not worried about that right now. We're just worried about the efficiencies, and we have everything for that. But what we do not know about the efficiencies is Carnot efficiency, right? This is the unknown. All right. So we can state some assumptions. What assumptions are we going to state? Well, they've said the system is 18% efficient. Let's see, what other assumptions could we can state that this system, T hot and T cold, is isothermal. So we're not considering anything being transferred beyond what we have stated here, meaning we can assume that, and we can also assume it's adiabatic. The reason why we can assume that it's adiabatic is because we're not considering entropy. So isothermal and adiabatic. Those are our assumptions. All right, so hopefully we can think about all this, and we'll go to the next one. So instead of so we're going to say this is T cold on this side, which is 60 degrees F. And this is T hot on this side, which is 340 degrees F. And this here, this control volume that you're looking at, is just another representation of the messy drawing you saw on the previous slide. Does everybody get that part? So this,
Yep.
okay, is equal to my messy drawing here. So when I say isothermal, I'm saying no heat is transferred from here to here. This does not happen. And I'm assuming that this process from here to here can also go this way without suffering from the laws of entropy. Therefore, it's adiabatic. All right, so now let's solve this. So we know that T hot is 340 degrees. So 340 degrees plus 460 is what?
What was that again?
340 plus 460 is 800, right?
Mm-hmm.
T cold is
520.
520, so 520 R. Therefore, so T hot minus T cold divided by T hot is equal to 0.35%. Now, what was the efficiency that they said they had?
18%.
18%. Now, does anybody wonder why that is what it is? It's very interesting. It's really kind of interesting. So, I don't know, I find it interesting. So, 18% is the efficiency of the system and 35% is the maximum efficiency, but it's not getting there. So let's see why. Okay, so now we're looking at an actual TS diagram. And our Carnot efficiency is here. Okay? But for some reason, not just for some reason, probably limitations in their system, this is what they have to go through in order to get their process done. So remember, we're going to skip back and forth on a couple slides here just so we all can see this. But this is the process that we're going to. Here's from 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Okay, what is 1 to 2? Remember what 1 to 2 is. It is,
Compression, right?
all right, so let's just, you guys can just help me remember and we'll talk about it. Because I'm too old to keep things in my head. So 1 to 2 is compression. So that happens here. 1. No, that happens on the feed water tank. So from here to here is compression. So then we start from 2 to 3. And remember, it says heat is being added to the system, right?
Mm-hmm.
Okay. So heat is added to the system. And that's where it's added here. So heat is added here. And it's still being compressed, right? Because heat is added and movement is starting, so it's still a compression. So that's from 1 to 2, and then we go from 2 to, and then we're going to go from 2 to 3. And notice there was some interesting here is that number 1, we started where it would be perfect Carnot efficiency, but in actuality, we started out here outside here on the vapor dome, right? So notice where the vapor dome, notice where the Carnot efficiency is always located, right in the middle of the vapor dome. So at these top points here to here, this is where you can get your maximum efficiency inside of the vapor dome. Okay, so then 3, this is also, this, you know, we're just traveling here, but this is also 3. And then from 3 to 4, the fluid expands and it shows it moves up, right? Well, because we have entropy involved. So entropy increases. So the fluid expands, turns the turbine, and now it goes into the condenser. And then the condenser, notice it doesn't go as low as we would have liked it. It still stays, a mixture with a high quality of steam or vapor, but it does not go all the way down to the bottom of the heat sink. All the power available in the fluid that went through this turbine did not get used in the turbine. So anything under here was unusable heat. Now, based off of the fluids that we use, these working fluids that we use, that determines where it's going to go on this TS diagram. And there's not one fluid out there that we could use that we are going to be able to use all the energy available in it, even when it comes to the limitations of Carnot efficiency. So working water as a working fluid is what we use a lot of, but we still do not maximize the energy use of it because, I mean, we physically can't. So, but anyway, so it goes from 4, and 4 goes to condenser, and then it goes back to 1. Same cycle every time. But as you can see, this thing got really trimmed right here. And then we still had to put energy in it from this point. Why do you think it started back down here when it comes to the real cycle?
Because that's when it's heating up from a resting.
Heating up from where?
From a resting temperature.
Yeah, from the room the room temperature. It started at, this is T60. This is actually T cold. So water comes into the pump. What they're saying here is that water actually comes into the pump at T60 at the cold temperature. So they're saying that there's a feed water tank here and there's no mixing. So I just wanted to see if somebody would catch that. from at feed water at T cold. It quickly heats back up though. All right. Well, is there any questions about Carnot efficiency?
Sort of.
Sort of. Okay.
I mean, I'm getting how to do it now. Yeah, I'm understanding this, but I'm peeking at the homework
Yeah.
or the final lab, and it's given us a value of the temperature of the surroundings. I'm not seeing exactly where that fits in.
Let me see what it says.
So it gives us the end temp, out temp, and then also a surrounding temp.
The in temp, out temp. Is the surrounding temp lower than the in temp
Yes.
and the out temp?
Yes.
That must be your heat sink.
Because they both are they're both steam entering turbine problems.
Yeah. Yeah.
One, it's entering as a higher value and exiting as a lower value
But the surrounding is still lower than the lower value, right?
by a substantial amount for both of them.
Yeah. Yeah. It's
So
kind of like this problem, right? Except you got to do some solving of the actual problem and you got to find out the efficiency. It kind of doubled it up in that problem. So you're getting to practice. You're getting to practice first law thermodynamics, and you're going to use the second law Carnot efficiency.
okay.
Does that make sense, Nathan? Like, so just think about this problem we just looked at. In that problem, you're not thinking about anything. Let's just say you're focused on the efficiency part of that problem. If you're focused on the efficiency part, and from what you just explained to me,
Oh,
okay, you get it now?
I get it. I get it. So like the two values are for the first law, but the 60 is for the second law. Okay, I get it. Okay.
So you're using the two values for the first law to find out the energy transfer, but then you're using the second law to see what the maximum efficiency is.
Yup. I get it.
Okay,
Thank you.
no problem. So yeah, the homework is it's a little rougher. It's just two problems, but I wanted to get you kind of ready for the final because the final ain't gonna be no walk in the park. You guys, and I don't want you to wait until Thursday to start it. Hey man, look, just because I've been breaking my brain and working problems for the last decade. Okay, and I don't know if you're a geek like me, which I don't know if you are, but I know that I pick on something and I can't let it go because I don't like being wrong and I like to figure things out. So I recommend that you take a look on Tuesday, read the problem, think about it, go about your day, think about the problem. You know what I mean? Like you don't have to do it all at once. If you get stuck, don't beat yourself up. You guys actually have how many days? 4 days to complete this. So, I mean, you have time. So your strategy can be different, meaning you get frustrated, you don't have to sit there. It is finals week, so hopefully you plan to give this stuff some time, but it's not something you're going to be able to sit down and do in one sitting. I mean, you could. Yeah, you could. I'm not going to lie to you, you can. But I want you to learn the most, so that's just my 2 cents. All right, guys. Well, it's been great. It's been a good term. Hey, did you get any type of review stuff or like some type of class asking if you guys would do a class?
Yeah.
All right. Hopefully
I got
you
a
take-
couple emails about class evaluations. Yeah.
All right, good.
I have a question about the homework that was due today, but I was late, so I wasn't able to ask it.
Okay, what's up?
Was question 3 supposed to be missing mass?
Let me see. Question 3, huh? Nuclear facilities, BTU study as a complete cycle. He produced his BTUs value. He removed from it. Said the pump is 200 feet below low. What is required pumping power to maintain a stable temperature?
Because I wanted to figure out potential energy. What? I wanted to figure out potential energy, but there wasn't a mass given.
There wasn't a mass given. That's true. Let's see.
I made the assumption on mine to just neglect it.
Yeah. BTUs per hour. It says it gives you a study the complete cycle, heat source, heat remove. I think neglecting it would be a solid choice. That wasn't on purpose though. That was a mistake on my part. If I'd have mentioned the working fluid, and a couple more properties, internal properties about the fluid, then you could figure out the mass, but I didn't mention that.
Mhm.
But that was a good question.
All right, that's all I wanted to ask.
All right, I'm gonna remove that from my questions now. The pumping flow stuff. All right, any other questions?
How many questions are on the final?
I don't know yet.
Oh, okay, cool. There's gonna be about that many.
About that many.
All right, take care, everyone.
Yeah, you take care too. I'm going to when it comes to the final is I need to go look back at the midterm and I'm gonna make my assessment from there, meaning how many questions there will be. And,
Okay, fair enough.
yeah, so
Alrighty, so once again, David, I appreciate your time. It has been a good term, and I thank you.
well, thank you for being a good student. I appreciate it. You guys are all pretty good. Everybody who hung in there. You guys are
That's
all
right.
you guys are all great.
Alrighty, thank you, David. You have a good one, and
You too.
enjoy making the test, man.
I will. All right.
Speaking of
Talk to you
Alright,
later.
bye.
I'm
Take
actually,
care, everybody.
but speaking of hanging in there, I'm actually gonna be able to get that assignment in now. It didn't take me nearly as long to make the adjustments I wanted, so it is getting turned in as we speak.
Isaac, I don't think you really have to worry about. You're doing all right, right?
I'm doing all right. I'm not too worried about like whether I'll pass the class. It's just I'm kind of like how you're talking about geeking out. I'm very particular about trying to get everything right,
Yeah. Good.
at least as close as I can.
Yeah. Geek out, man. Geeks rule the world.
Yeah, I will be see y'all later, but yeah, you'll see that assignment pop up in like 5 minutes.
Great. I'm gonna grade it on Saturday. Everybody, I grade on Saturday. I'm gonna grade both of them on Saturday, and then you're gonna have the final on Tuesday morning.
Heck yeah, sounds great.
You know where you stand, and we'll get her done. All right. You guys have a good night. Talk to you soon.
Awesome. See you later.
All right. Bye bye.